There are four blind spots in modern systematics. First is theory. Evolutionary analysis does not provide theory. You have to do so. An example is pseudo-extinction, as modeled by a cladogram. Second is what correct means. Correct refers to that variant of the model that best follows your theory. For example, which cladogram? Third is the probability of the hypothesis. This simply tells you how much better the best hypothesis is than the second best hypothesis. Bayes factors are used for this. Fourth is that monothetic genera are artificial. In fact, it is entirely possible to split large polythetic genera into units of one ancestor and a few descendants, all sharing the same basic traits. The analytic methods used in cladistics only allows choices between various cladograms. The best cladogram is the one that best explains the data. On the left is an example cladogram. In Bayesian analysis, the formula combines prior information with a likelihood of the data. In cladistics, the choices between cladogram branches is based on the likelihood alone. There is no prior, or the prior is flat and uninformative. A cladogram is a dichotomous first-order Markov chain. Also, the ancestral species and their descendants are terminal on the branches. Macroevolutionary analysis also uses Bayesian analysis. The ancestral species are placed inside the cladogram. This is called a cologram, a stem taxon dendrogram. The ancestral species then provide information for a Bayesian prior. Because both the informative prior and the likelihood are used, it is a second-order Markov chain. The cologram is better than a cladogram because it is theoretically more realistic and the statistical analysis is far better. A species is here divided into two parts. The novan is the set of all the new traits developed during speciation. The novan prepares the species for insertion into a different ecological niche. The ancestron is the set of all traits of the ancestral species that are not changed for use in the novan. The immediate ancestron is the set of traits given to the ancestor by its own ancestor. The traits of the immediate ancestron are probably adaptive for survival in its immediate environment. We now ignore the train of ancestral traits that are not presently useful. There are two species modeled here. There is the ancestral species, which is in blue and green, and one of its descendants is in yellow and blue. The yellow is the novan of the descendant, consisting of state changes of otherwise useless traits in the ancestron. The blue is the novan of the ancestor, which is the same as the immediate ancestron of the descendant. The blue traits are almost always given exactly the same to all descendants. Sharing this immediate ancestron helps define a monothetic genus. A monothetic genus is one with one ancestral species and a few descendants, all with the same immediate ancestron. The ancestor's ancestor, novan, is in green. It is given to the descendant's ancestor. The ancestor's ancestor may be considered an outgroup. The novan of the ancestor is in blue and is given to the descendant. These two species are in-group. The ancestor's ancestor is the outgroup. Determining which species of a monothetic genus is the answer is by similarity with the outgroup and by being more generalist than the other, more specialized species of the in-group. In my book on fractal evolution, I used NK analysis with a random Boolean network model to determine that 4 descendants are the optimal edge of chaos number of species in a monothetic genus, and each species optimally had 4 traits in its novan. This is a diagram showing X as the outgroup. The ancestor A creates a novan in blue that it gives to all 4 descendants. This may allow them to survive best in the ancestor's home region, that is, sympatrically. The descendants develop their own novans for survival in some potential allopatric niche. All of this is powered by natural selection. A dendrogram with ancestors inserted at nodes allows computation of Bayesian support. The diagram shows 4 new traits per speciation event, which is the optimum number for the edge of chaos. The prior in Bayes' formula is the number of new traits generated between the ancestor's ancestor, in green and white, and the monothetic genus's ancestor, in green and blue. The likelihood, or conditional probability, is the number of new traits between the ancestor and its descendant species. These are treated as Shannon informational bits, or powers of 2. These are also log likelihoods, which can be added. The sum is 8 bits. The odds table on the right tells you this equals a Bayesian posterior probability of 0.996, which is quite high. But how much better is 0.996 than the Bayesian posterior probability of an alternative hypothesis? To create an alternative hypothesis, we switch ancestor with descendant. There are 4 reversals now in each speciation event, which add to -8. The Bayesian posterior probability of -8 from the odds table is 0.004, quite low. Well, how low is it? We calculate the Bayes factor, which is one posterior probability divided by the other. This is 249. Any Bayes factor higher than 20 is strong support. I did an analysis of species in the Weisier relationship in the West Indies and adjacent regions. Here is the cologram showing segregate monothetic genera. The 3 monothetic genera, each in separate color, are largely bursts of 3 or 4 descendant species. One of the descendant species has also generated 2 other genera with different immediate ancestrons. This may be punctuated equilibrium, at least in evolutionary time, if not also in geologic time. The West Indies arose in mid-Miocene, relatively recently. This is a different lineage in the trichostomum relationship in the West Indies. Here are the 4 monothetic genera in separate colors. Each are largely bursts of optimally 4 descendants. Could it be that the interactive processes leading to the optimality of the edge of chaos generate punctuated equilibrium? Some monothetic genera that are widespread in the world have secondary ancestry. Here is Anactangium, a widely distributed genus showing non-punctuation or anagenetic macroevolution. The secondary speciation is a combination of new states of very old traits in the ancestron and modifications of new traits in the nova, where the asterisks are. This may be explained as successful establishment in geographically rather distant allopatric niches. Why is this important? Because the details of past adaptational evolution are valuable in predicting events during the present biodiversity crisis. The double niche macroevolutionary theory is based entirely on natural selection in a complexity context. A monothetic genus in a generative niche provides optimally 4 descendant species, each provided with the same set of immediate ancestron traits. These shared traits allow survival in the ancestors' sympatric areas. The descendants, with an example in blue and light green, pass down a transient path. They follow a gradient of increasingly optimal niches for their novan traits, perhaps following steps of a 4 to 6 degree of separation. The descendants finally end up in an entropic niche, where they share their novans, in light green, with species from other genera. The entropic niche is where ecosystems dissipate entropy to avoid major environmental perturbation. I suggest that emergent processes presently investigated by complexity theory are the same in both generative and entropic niches. I predict that the fractal dimension of 1.16 will prove the same for generative and entropic niches. More information on this method may be found in my book on fractal evolution and in a preprint entitled Monothetic Genera are the Cast Iron Building Blocks of Evolution. They are both available free on the web. Thank you.